4.8, number 361. We have the limit as x approaches a of x minus a over x to the n minus a to the n. All right, there's two ways to approach this problem. One is L'Hopital's rule, which is what this section is all about, so it makes sense to do that here, and I'll show that in one moment. And to confirm that we can use L'Hopital's rule, let's see what happens here. As x approaches a, we get the numerator approaching a minus a, which is of course approaching 0. And as x approaches a, we get the denominator approaching a to the n minus a to the n, which is of course approaching 0. So it is indeterminate form to which L'Hopital's rule applies. There is another way to view this particular limit, and many of the questions in the textbook are like this. That's something to watch out for. If I said f of x was the nth power function, and I said, let's find the derivative of this function at a, then by definition of the derivative, I would have the limit as x approaches a of this power function minus the power function with a plugged in over x minus a. That would be the definition of the derivative for this particular function. Okay. Now we've kind of moved away from the definition of derivative because we have all these derivative rules now, but still, if I compare this definition of derivative for this particular function with the limit I have here, right? So this and this look remarkably similar. The only difference is I have the reciprocal of what's sitting here inside the limit. So if I did complete this, I know what I would get using the power rule. I don't have to do any algebra on this. I know from the power rule the derivative, right, of this function at a would be n, right? I'd bring the power down. I would have x to the n minus first power, right? Lower the power by 1. Then I would fill in the number a in for the variable. I would have n a to the n minus 1. That is what this derivative is and this particular limit is. So if this limit is n a to the n minus 1, then the reciprocal, right, which is what I see here, of this limit must be 1 over n a to the n minus 1. So that's my belief here. Think about it in terms of the structure of a derivative definition. This must be nothing other than 1 over this result, n a to the n minus 1. Okay, that may not be the most obvious thing, and we're also supposed to start practicing L'Hopital's rule, so let's go ahead and do that and just show you it ends up being the same thing. But again, there are different ways of thinking about these limits, and you want to become comfortable with all of them if possible. Okay, so limit as x approaches a of x minus a over x to the n minus a to the n should be, through the use of L'Hopital's rule, right, the same as the limit as x approaches a of the derivative of each of these quotiented out. So the derivative of x minus a with respect to x, right, the changing object here, a is just a constant throughout this whole thing, and so is n. They're both constants. So the derivative of x with respect to x is, of course, 1. The derivative of negative a is 0 because it's a constant. The derivative of negative a to the n, negative a to the n, is also going to go to 0 because it's a big constant. But the derivative of x to the n will be n x to the n minus 1. Right, just using the power rule on an abstract situation, right? An abstract power function, and then you get the abstract power rule here, n x to 1 power less here. So now we can plug in a for x because nothing is heading towards 0 anymore. There's no concerns here. So we just plug a in, we get 1 over n a to the n minus 1. That'd be exactly what I suggested from looking at it through the lens of the definition of derivative. But the book's probably expecting you to do this move here using L'Hopital's rule. Just be aware of what's constant and what's not. and then the derivative will be pretty easy to take.